Welcome to Pomodoro Joe for Monday, March 6th, 2023. Today we're looking at LeetCode problem 1539, kth missing positive number. We got an easy one today. So, given an array of positive integers sorted in strictly increasing order and an integer k, return the kth positive integer that is missing from the array. That's actually not an easy problem. I would call this a medium, but here's an example. The array that we're given is 2, 3, 4, 7, 11, and the k is 5. So we're looking for missing number 5. And it looks like we're missing numbers 1, 5, 6, 8, 9, 10, so on and so forth. So the fifth missing number is 9. Okay, so this is actually pretty tricky because we're not looking for a specific number, like a number that's actually in our array. We're looking for a number that's not in our array. So that's going to be tricky. All right, we'll put 25 minutes on the Pomodoro timer and get started. So for this one, I think what I would do is, because we're looking for a number that's not in the array, I'll keep track of what is the expected number. What number am I expecting to find? So let's start with that. And so the first expected number we have, if we look at our example here, is the number 1. So now we can go through our array and say, is the number in the array the expected number? If it's not, then we can add this expected number to some list of missing numbers. So let's also keep a list of missing numbers. And it's just an empty list to start with. Okay, what else do we need? Well, we need to know where in the array we're looking. So we'll also keep an index. And we'll start at index 0 in our array. All right. And what else do we need? Well, let's start with these pieces. We have an expected number, a list of missing numbers, and some index that we're looking at. Okay, so how do we know we're done? Well, let's see. We're going to loop through all of the numbers in our array, but we only know we're done when our missing numbers list is greater than or equal to k. So the number of elements in our missing numbers list. We have at least k elements in the missing numbers list. Let's put it that way. All right, so while the length of our missing numbers list is less than k, then we have to keep going. Okay, and then how do we do this part? Well, we say, well, let's look in our array at our index, and if that is not equal to our expected number, then we'll add this expected number to our missing numbers list. Okay, so if the array at our current index doesn't match the expected number, then we're going to add that expected number to the missing numbers array. Okay, now at some point in here we need to change our expected number and our index. So let's do that here. Let's see, if the array at our index is not equal to our expected number, then it must be greater than our expected number, because it's already saying here that this is a strictly increasing order, which means that every number in the array will be greater than the previous number in the array. All right, so if our array at the index that we're looking at now doesn't equal the expected number, well, then we don't want to change our index because our expected number must be lagging behind. So let's only change our index if they are equal. And then we could say index plus equals 1, but we will always be changing our expected number because every step along the way we're expecting the next element to be the next biggest number. Okay, now there's one thing that we're still missing here. What happens when we get to the end of our array? Well, our index will be out of bounds, so we have to make sure that we're not going out of bounds here. So let's see. All right, so let's check to make sure that our index is not out of bounds. If it is out of bounds, then we can go ahead and add this number as a missing number because it's not in our array. Otherwise, if it's in bounds, we will check the array to see if it matches our expected number. And then our expected number will keep increasing. And then at the end, we will have some list of missing numbers. And so what do we return? Well, we'll return the last number in that list. All right, so I think this should do it. So again, we have an expected number that starts at 1, and every step along the way, we expect the number in the array to be 1 plus that previous number. So we'll keep incrementing our number every time. When we have enough numbers in our missing numbers list, if we have k numbers in our missing numbers list, then we know we've found the kth missing number, and we can return that number. All right, how do we find that missing number? Well, we check to see if the expected number matches the number in the array. In this case, we're saying if it doesn't match, then we'll add that number to the missing numbers list. All right, let's see if this works. So it works. Let's see if we can pass all of the runtime tests. And we pass. And it's not too bad, actually. So we pass, beating 86% for runtime and 98% for memory. So that's actually a pretty decent algorithm. Okay, let's see if we can improve upon this. So in this one, we're actually keeping this list of missing numbers. Do we actually need to keep this list? Well, this expected number will actually be the missing number, the kth missing number. So we don't need to actually keep the entire list of missing numbers. We could just keep a count of missing numbers. So let's call this the missing numbers count. And we'll set it to 0. And while the missing numbers count is less than k, then we'll keep doing our same algorithm. But we don't have this missing numbers to append. So in this case, we'll just increment our count. So instead of appending to a missing numbers list, we will just say missing numbers count plus equals 1. Now at the very end, we don't have this missing numbers list, but we do have a count. Now the count's not going to help us here. It's the expected number that helps us. So at this point, our expected number didn't match. We increment our count, which means that that expected number is the missing number that we're looking for. However, we've kind of overshot that number by continuing this loop. So we need to actually do the expected number minus 1 as our return value. Okay, let's see if this works. Okay, that works. Let's see if this saves us anything. It should save us a little bit on our memory. Not really. So we're at 83% for runtime and 80% for memory. So that's a change of 86% for runtime and 98% for memory. So we actually do worse with this algorithm. That's a little bit surprising. Okay, there are other things we can do here. And if you're interested, I'll show you how to do them. You can stick around. If not, you're totally fine to go try this one on your own. Again, this is 1539. It's totally worth checking out. So what other things can we do? So with this one, we're actually keeping track of what our expected number is and comparing it to the number in the array. But one thing to notice is this tells us this is a strictly increasing ordered array. We're looking for the kth positive integer, and there is a direct correlation between the index in the array and the expected value in that index. So let's actually go back to our code here. So our expected number starts at 1 because we're expecting our array to start at 1. Now the next number we're expecting to be 2 and 3 and 4 and 5. Now the index of those numbers, so if you look at our expected value 1, that's at index 0. Our expected value 2 is at index 1, and 3 is at index 2. So basically our index plus 1 is the expected value at that index. So there's a direct correlation between the index in the array and the expected value. So if I were to ask you, well, what's the expected value at index 100? You don't have to think, well, I need to go from 1, 2, 3, 4, 5, 6. You can just say the expected value at index 100 is 101. So if we know there's this direct correlation between the index and the expected value, then what do we find when we're missing numbers? For example, in this example here, if we start at 2, but we're expecting index, let's see, this is index 0, we're expecting value 1. So our value because we're missing a value, is going to be ahead of the expected value. So we're expecting 1, we get 2. And in here we're expecting 2, but we get 3. So this kind of tells you, I guess, how do I put this? This gives you a hint of how we can detect when we've reached the kth missing value without actually having to check for expected number necessarily. We can just look at the difference between the index and the number at that index. So let's try to do this. Okay, so now that we know that there's a direct correlation between the index and the expected value, we can rearrange our code to make it a little bit more efficient. So let's try something like this. We'll still start our index at 0, but we'll have our expected value be our index plus 1. Now we'll also keep track of the delta between the expected value and the actual value at the array. Okay, now if the array has the value we're expecting, our delta will be 0. If the array has a higher value than what we're expecting, that means we know we're missing some values in between. So for example, in this case, we're at index 0, we're expecting 0 plus 1, but we're getting 2. That means we're missing the value 1. Now we don't necessarily know which value we're missing, we just know that we're missing a value. So as long as we have a delta that's less than k, that means we're missing fewer than k values. So that's what our loop will be looking for. Delta's less than k. So while the delta is less than k, then we can increment our index, and we can increment our expected value. And we can recalculate our delta. All right. Oh, but there's one other thing that we're missing here. So we still need to make sure that we don't go outside the bounds of our array here. So while the delta is less than k and our index is less than the length of our array. All right, and then here, because we're incrementing our index first, we need to do a second check to make sure we're not exceeding the bounds. And then once we find that we've got an index that basically has a delta that's greater than k, greater than or equal to k, that means we've found the index where the missing piece should have been. So what do we return? So in this case, we'll return that index plus the k missing piece, or missing elements. All right, let's see if this works. Okay, that works. Let's submit this. And we pass. We only beat 47% for runtime and 80% for memory, but hey, that's not too bad. As you can see, I did re-record this just because I didn't explain it very well the first time I ran through it, so I thought I'd try again. All right, let's go back and see what's going on here. Okay, so how do we improve upon this? Because clearly this wasn't the best algorithm. We could clean this up a little bit, so let's try to clean this up just to make it a little more streamlined here. So we don't need to actually keep these intermediary values. We can just keep index. So in here, the expected value, this is just index plus 1, right? So any place where we had this delta, we can just replace it with this. All right, so our delta gets replaced, and we can eliminate this here because now we're calculating it in the while loop itself. And we don't need this expected value anymore because we're just using the index directly. That means we don't need these. There, much cleaner. So now this is our delta while it's less than k, and while our index is less than the length of the array. We'll increment our index, and then at the very end we can return our value. Let's see if this still works. Oh, I need to do my length check first. So that's right, the order does matter here. So we need to check that our index is within the bounds before we try to use it. So just to be clear, I'll point that out. So in this case, we're checking the index first. If this succeeds, then we can check this second condition. If this fails, then we don't even bother checking the second condition, and we can avoid essentially an out of bounds check here. Whereas if we did it this way, if we did the first check, if we did this check first, this index could be out of bounds. We don't catch it because we haven't checked it yet, and we'll have an out of bounds exception. All right, so let's get these in the right order. Try that again. That works, and we'll submit that. 60% runtime, 80% memory. Not bad, not great, but not bad. Okay, now the final piece to this. Now that we understand that we can use the index as essentially the indicator of what value we're expecting, we can do a binary search. We can say, jumping to a particular index, we can essentially know what we're expecting to find here, and we can see how far off we are from that expectation, and we can adjust the bounds of our binary search accordingly. So let's do that. So instead of having an index, we're going to have the bounds of our search area. So we'll have the lower bound, which will be 0, and we'll have the upper bound, which will be, let's see, the length of our array, -1. So that's the last index in our array. Okay, now while our upper bound, so in this case, we're basically finding where did the low and high converge, and we'll be searching for the k delta every time through this loop. So we'll say, while our upper bound is greater than our lower bound, we'll find the midpoint. And so the midpoint is just the lower bound plus half, basically. And how do we calculate half our range? Well, that's going to be a high minus the low, and we'll do an integer divide by 2. So this gives us our midpoint. Now we can use that same algorithm that we used last time to figure out if we have k missing elements or not, by saying, so if the array at this midpoint minus, and again we need to look at our index plus 1, that's the expected value. If that is less than k, that means we haven't found k missing values yet, so we'll increase our lower end to our mid plus 1. So now we'll go between mid plus 1 and the upper end. Otherwise, if we have found at least k missing values, we need to lower our high end down to mid minus 1. So I'm not explaining this super thoroughly. This is a standard binary search. If you have questions about this, you can leave them in the comments, or you can check out some, let's see, I'll see if I can link some helper documents in the description below, so you can check those out. Okay, so this is your standard binary search. While the high is greater than low, we'll be adjusting our low and a high. And at the very end, we will have some return value, which will be our low plus our k. So just like we had index plus k before, it'll be low plus k in this case. All right, let's see if this works. Okay, oh, looks like I don't have an index, that's why. This is mid plus 1. All right, that was a silly mistake. Another silly mistake. There we go. Okay, let's try that. All right, and we passed, beating 88% for runtime and 80% for memory. Not too bad. So my best so far was this one here, which is basically the same algorithm. So I don't know why it's not doing as well this time. That's interesting. Yeah, this is virtually the same algorithm. Let's just copy and paste this in and see what's the difference. So I still have a low, I still have a high, high greater than or equal to low. Yeah, this is literally the same algorithm. I don't see any difference. That's interesting. So that makes me question the numbers from the analysis at the end, because these are literally the same. One gets a 90%, the other only gets an 80%. Kind of makes you wonder. Let's try this. Yeah, 83%, same algorithm where I ran before, and I was getting a 95%. Huh, curious. All right, well, I think that's it for me. Hope you enjoyed this, hope you had fun, hope you learned something, and hope you can go out and write better code.